Welcome. In last few sessions, I tried to introduce Jacobian Gauss-Seidel methods, which are the basic iterative solvers, and then we also discussed about the properties of the matrix A for which these solvers should work, and we have seen that the matrix has to be diagonally dominant or irreducibly diagonally dominant. That means diagonally dominant means all the diagonal terms must be greater than sum absolute value of all the diagonal terms must be greater than sum of absolute value of the diagonals for each particular row. And diagonal irreducibly diagonally dominance means that sum the all absolute value of a diagonal term must be greater than equal to sum of the absolute values of the off diagonal terms for each particular row, and there should be at least one row for which it is not greater than equal to, rather it is greater than the sum of the off diagonal terms. The absolute value of the diagonal term is greater than the sum of the absolute value of the off diagonals. And for these cases Jacobian Gauss-Seidel works, and Jacobian Gauss-Seidel works for these cases because we looked into the iteration matrix G. Iteration matrix G will have a spectral radius less than 1, which will ensure that the matrix norm of G will be less than 1, and as we will do a number of iterations, the initial error which will be multiplied by matrix norm of G to the power k, k is a large number, which this will be a very small number, therefore, it should converge, the error should be very close to 0 and it should converge to the right solution. And if it is converges, that means if the guess and after now large number of iteration the solution converges, that means the guess and updated value has very small difference in between them, it must converge to the right solution. That is also a property of Jacobian Gauss-Seidel. So, now what we will do? We will do some numerical experiments using Jacobian Gauss-Seidel. We also introduce the terms convergence rate, convergence factor, and have seen that it depends on the matrix G, it depends how we are splitting the main matrix A. The only condition for the we are solving x is equal to b, the only condition on the main matrix A is that it has to be diagonally dominant or irreducibly diagonally dominant. Now, it depends how are we splitting the matrix A to get the matrix G, and based on that we will get the eigen values of G. The largest eigenvalue is the spectral radius, which is also a measure of the convergence factor as well as convergence rate of the iterative scheme. So, and it will tell us how fast the iterations will converge. So, what will we do is called numerical experiments. That means, we will take few matrices and do experiment with these matrices. We will try to run Jacobian Gauss-Seidel on these matrices, as well as we will see how are their G matrices, what are the spectral radius of G matrix, what is the convergence factor or convergence rate. So, that we can say a priori looking into the G matrix, we should be able to tell that whether they will converge fast, whether they will at all converge or not, etc. So, for these numerical experiments, we have chosen a particular matrix, which is the matrix generated as finite difference approximation of d 2 t dx square is equal to 0. We have discussed about how to convert a differential equation into a matrix equation, exactly that has been done here. At the boundary condition t x is 0 to 1, boundary condition is t is equal to 0, it is 0, t is equal to 1, that value is 1. And we now, so this will give essentially a tridiagonal system. We varied the number of intervals and got large number of points and got larger matrix systems. So, a tridiagonal matrix is obtained. Matrix size is varied by varying the number of grid points and number of intervals, and we got different matrices, but the matrices will essentially look like a tridiagonal matrix. For this is an example of a 8 by 8 matrix. However, here we consider 10 by 10, 20 by 20, 40 by 40 matrices, and then with this matrix we ran a Gauss-Seidel or Jacobi program. Later we will also discuss how to write these programs, how to implement a Gauss-Seidel or Jacobi into a computer program. We ran a program and noted what are the number of iterations to solve it. We also noted into the G matrix which comes out of. So, this is basically how the A matrix looks like here. but this is 8 by 8, we have taken several matrices. So, seen how is the G matrix and then try to find out the eigenvalues of the G matrix from which we can get the spectral radius and see how is the convergence property. So, matrices are solved using Jacobian Gauss-Seidel method, because this is doing experiment with the matrices and the method, and but this is not experiment in hardware, we call it numerical experiment. The spectral radius of matrix G, convergence rate is minus logarithm of the convergence factor of the spectral radius, and the number of iteration are noted for different sizes of the matrices. So, for 10 by 10 matrix, for Jacobi iteration the spectral radius is 0.94632. For Gauss-Seidel the spectral radius is 0.89533. So, for Gauss-Seidel the spectral radius is smaller. The convergence rate is 0.05517 for Jacobi, and for Gauss-Seidel is 0.11034. So, the convergence rate is almost double in case of Gauss-Seidel than Jacobi, and this is due to the fact that the spectral radius is smaller. So, if the convergence is double, the rate will be double, speed will be faster. So, the number of iterations will be small, faster it will converge, and we can see that this is almost half. If we need 200 iterations for Jacobi, for Gauss-Seidel we need 106 iterations. So, there is a relation between convergence rate and number of iterations. Roughly if we multiply convergence rate with number of iterations, there that is roughly constant, at least in this case. In other cases we will also see, at least for same size of matrix. So, once we have a method in a Gauss-Seidel, we have a lesser spectral radius, therefore, the convergence will be faster, the number of iterations. So, rho g is also convergence factor, right, rho g is also convergence factor. General convergence factor. So, if this is smaller, the iterations will we need less number of iterations, the scheme will be faster. Now, we go to 20 into 20, we can see similar thing. The spectral radius of Jacobi is 0.98645. So, we will need not lot more iterations, spectral radius is very close to 1. The convergence rate is 0.101364, Gauss-Seidel spectral radius is 0.973, convergence rate is 0.027, and the number of iterations are again almost close to half of each other, 709 in Jacobi and 374 in Gauss-Seidel. And now, we can also see the also you can see that for convergence rate in 10 into 10 Jacobi is 0.055, right, and in Gauss-Seidel is 0.013, it is nearly 4 times, convergence rate is reduced by nearly 4 times, and iteration number is increased by 3.5 times. So, there is a relation between convergence rate and iteration number for similar type of matrices. If we increase 40 into 40, the Jacobi spectral radius is very high, 0.99661, convergence radius is 0.0034, Gauss-Seidel 0.99324, convergence radius is 0.0068. So, because the iteration number is very high, I think this is swiped, this will be, I will change that in the later slide. This is 2435, this is 1291, this is swiped while making the table. So, because the iteration spectral radius is very high, very close to 1, we need a very large number of iterations, 2435 iterations here, and in Gauss-Seidel we need, it is also high, we need 1200 iterations. So, as the spectral radius is increasing, we are also needing larger number of iterations. However, Jacobi consistently give larger spectral radius than Gauss-Seidel, and it consistently takes more number of iterations than Gauss-Seidel, and the convergence rate is reversed in both the cases. So, the observations are largest eigenvalues or the spectral radius increases with matrix size, matrix 20 into 20 eigenvalue, largest eigenvalue is more, and spectral radius is, and because largest eigenvalue increases, spectral radius also increases and number of iterations are more. Spectral radius is higher for Jacobi than Gauss-Seidel, and we when proposing Gauss-Seidel, almost intuitively you propose that if we can use some of the iterative values, some of the updated values, the iterations should converge faster. So, this is an almost intuitive, actually intuitive proposition. However, we can see that it is actually giving faster convergence, and why is it giving faster convergence? Because in the iteration matrix level, the spectral radius has been reduced. Well, the third observation is that number of iterations required for convergence is strongly related with convergence rate. Almost, if we have like here, convergence rate is almost twice for Jacobian Gauss-Seidel, and the number of iterations is again almost half in Gauss-Seidel compared to Jacobi. So, largest its convergence rate and number of iterations are related with each other. For a same matrix, Jacobi gives higher spectral radius, therefore, slower convergence rate compared to Gauss-Seidel, and as we will increase matrix size, the largest eigenvalue increases, convergence rate decreases. This is actually very important, the first observation, because we will come maybe at the very end of this course, when we will discuss about what is called multi-grid, we will look into large matrix size, issues with larger matrix size. But if we are increasing larger matrix size, we are taking lot of grid points. We are taking lot of grid points, we are doing less numerical errors in terms of the distribution error. However, the number of iterations increase and the computational cost increase. Why the number of iterations increase? Because the eigenvalue of the largest eigenvalue of the G matrix or spectral radius of the G matrix increases if we take large matrix. So, large matrix, many number of grid points will give us accurate result, but it will be a slow process and the computational cost will be high. So, now let us look into the convergence in detail. Let us run a Gauss-Seidel code for a diagonally dominant, a small matrix, a 3 by 3 diagonally dominant matrix. We will look into the convergence in terms of L infinity norm of the residual B minus x, and we will also look into the difference of x k plus 1 minus x k. The residual, initially we start with some guess x is equal to 0, first iteration. Residual is 1.24 and x k plus 1 minus x k is 0.45. In the next case, we use the updated x, the residual becomes 0.42 and the difference between x k plus 1 minus x k becomes 0.248. So, as this difference decreases, we can see as this difference decreases, the residual also decreases, and this difference decreases asymptotically. At the end, x k plus 1 minus x k is 10 to the power minus 9 and the residual is 10 to the power minus 8. We will say that the difference this has converged. So, x minus the difference between b minus x, which should be actually 0, is also practically 0, because we are solving a x is equal to b. So, this should also come to 0, as well as this also should go to 0 for convergence and accuracy. So, as the solution becomes accurate, the difference goes to 0. Now, you can make few observations from that both the parameters x k plus 1 minus x k plus 1 minus x k and residual, both these parameters monotonically reduce to 0. These are the L infinity norm, that is the largest value of the both these are vectors. So, largest component of the vector, both these parameters monotonically reduce to 0, there is no oscillation, it is never increasing, it is continuously reducing to 0. So, for Gauss-Seidel or Jacobi or all something like this direct basic iterative methods, the errors or the residuals must not oscillate, they must monotonically go to 0. If there is something different, if it is oscillating, then there is some problem in the implementation. Why? Because every time this residual is being multiplied by g to the power k, which is reducing the norm of the vector. The difference x k plus 1 minus x k is correlated with r is equal to b minus a x k, b minus a x k. As the residual and the difference is correlated, in a sense, if this is reducing, this is also reducing, like as the smaller the value of x k plus 1 minus x k is being, like this is smaller than this value, therefore, the residual is also smaller than this value. So, they are related. Interestingly, the residual as well as this difference, their rate of slowing down is not reduces with time. For example, here this difference reduces by 0.21. In the next step, this difference reduces by 0.17, something like that. Here this difference reduces by 0.3 into 10 to the power minus 7. Here this difference reduces by something order of 10 to the power minus 9. So, the rate at which the differences are reducing is also slowing down with number of iterations. So, if I say that this is the x star and I have started with x 0 and this is the number of iterations, this is x star, this is x 0, this kind of asymptotically approaches it, the rate slows down with time. This is an important observation here. However, so this is what we are getting using Gauss-Seidel, or this particular case is, I think, for a this particular case is for a Gauss-Seidel solver. This is for a Gauss-Seidel solver. For Jacobi, it will give similar result, but we will need more number of iterations. The rate at which the residual falls down is smaller because G has a larger spectral radius. However, so what you see that they are following certain pattern, and this pattern is determined by how is G, what are the eigenvalues of G in largest eigenvalue of G in Gauss-Seidel or Jacobi method. Now, our question becomes that can we improve it? Can we increase the spectral radius through some splitting? Will not be intuitively we found out one splitting which is Gauss-Seidel. Can we have some other splitting through which we can improve the convergence rate? How to improve convergence? Jacobi or Gauss-Seidel gives x k plus 1 is equal to g x k plus f. We will think of some, and this G comes out splitting of A is equal to m minus n, which is A minus D minus E minus f, or D minus E minus f, something like that, and then forming m inverse n as G. Now, we will try to A is equal to m minus n, m inverse n is equal to G, that is the idea we followed here. Now, if we try to improve convergence, that means if we try to take m and n in some different way, so that the G has a smaller spectral radius, can we do that? So, again we will start with some intuitive idea here, and we will see the effect in the spectral radius later. So, what we do at every iteration step is that x k plus 1 minus x k is equal to g x k minus x k plus f. So, after every iteration step x k plus 1, this is the iteration step, is modified, this is the error difference between consecutive guesses updates. The x k plus 1 is modified by this term g minus I x k plus f. Now, if I go to my previous slide, what I was looking here is that this is G minus I x k plus f. Why is it taking so much time for convergence? Because this value is reducing with each iteration. This value is not a large value, this is a very small value. Had this been a larger value, we could have achieved the solution, we could have converged to the right solution in a fast manner. Or I showed that this is approaching this the actual solution x star x 0 in something like this. Instead, if we can use some faster solution or some faster way to converge it. So, what we will do here, we will look into this difference, and if we can increase this difference, because every time we are trying to approach the final solution by adding some value with x k and getting x k plus 1. So, if what we are adding here is g minus I x k plus f in Gauss-Seidel or Jacobi. if we can increase this or if we can scale this. So, this is the difference that x covers in a particular iteration till it converges to the exact solution. If x k plus 1 minus x k can be increased at each iteration steps, number of iterations will be reduced. This goes through a very simple linear logic. If we can increase this value, then x k plus 1 will be further updated. So, it converges to the right result. There can be some cons also, it might not converge, it might diverge, it is increased so much that it is never coming back. Let us see what happens here. And this method is called a successive over relaxation, that you over relax the solution. You are updating the solution using some relation from the using gauge value, you are updating the solution. Increase the amount of update, update it more, over relax the update. So, Jacobi Gauss-Seidel step will look like this, and over relaxation step will be like this value is multiplied into omega g I, this is under a bracket, omega into g minus I x k and omega greater than 1. So, at each iteration step update x as x k plus 1 is equal to x k omega g minus I x k plus f, this will be plus f. This is under bracket. The SOR, if we write it down by d and I, SOR will be d minus omega I x k plus 1 is equal to omega f plus 1 minus w d x k plus omega b, and the iteration matrix or x k plus 1 is equal to d minus omega I inverse w f plus 1 minus 1 d x k plus d minus omega inverse omega b. So, it is nothing but this follow this step, x k plus 1 is equal to x k g minus I x k plus f. So, find out the updated value, what is the difference between the updated value and gex, multiply it by some factor omega which is greater than 1, and then add this with the guess value, this is your new update value. And this is equivalent to writing the matrix like this. So, the G matrix iteration matrix is d minus omega I inverse omega f plus I minus w omega d. In case omega is equal to 1, this is not over relaxation, this becomes to the Jacobi or Gauss-Seidel step. We can check that this is d minus E inverse f plus d, this becomes the Jacobi step in case omega is equal to 1. This is sorry Gauss-Seidel step, over relaxation is applied over Gauss-Seidel. In case omega is equal to 1, this goes to Gauss-Seidel. What happens in case omega is equal to 0? You can check that. So, this is d inverse f plus d, right, and f plus d is again d is equal to d minus E minus f is equal to a. So, iteration does not progress, it stops there, there is no update. So, what should be at omega is equal to 1 it is Gauss-Seidel, omega less than 1 it is under relax, the solution is becomes slower. So, omega must be greater than 1, what should be the right value of omega for which we will mark. For convergence we need the spectral radius of G less than 1. The theorem, if A is symmetric with positive diagonal element and omega is in between 0 to 2, successive over relaxation will converge for any x 0 if A is positive definite. This is a theorem like that. So, if omega greater than 2, successive relaxation will not converge, the theorem is not satisfied. So, it will diverge. If omega is equal to 1, successive over relaxation is same as basic Gauss-Seidel or Jacobi method. If it is applied over Gauss-Seidel, it is usually it is applied over Gauss-Seidel, because Gauss-Seidel is better method than Jacobi and we want to further improve convergence. So, we apply successive over-relaxation over Gauss-Seidel. If omega is less than 2, successive omega is less than 1, I am sorry, omega is less than 1, successive relaxation is actually under relaxing the iterations or increasing the number of iterations. So, the question is that omega should be between 1 to 2 for better convergence, omega for better convergence. So, the question is what should be the value of the omega? What is the optimum value of omega? And in that, in which case, and what is the optimum value of omega? When rho g is least, we will have best convergence rate. So, you have to either look into the G matrix and see with omega c when it is having the least over relaxation factor, least spectral radius. So, we said that that is the best omega. Omega is in between 1 to 2, in 2 omega will start diverging, in 1 it is same as Gauss-Seidel. So, best omega should be in between 1 to 2. However, there is one more theorem which helps us to determine what should be the value of optimum omega. If A be a consistently ordered matrix such that the diagonal element is non-zero, there is a definition of consistently ordered matrix, will not come here, but all these matrices we deal with is usually consistently ordered matrix, and omega is non-zero, and if lambda is a non-zero eigenvalue of the SOR iteration matrix G, there is a scalar mu which satisfies lambda plus omega minus 1 whole square is equal to lambda square omega square mu square, then mu is the eigenvalue of the iteration matrix Jacobi iteration matrix B. So, Jacobi iteration matrix eigenvalue and the SOR matrix eigenvalue are related by the term omega. So, and using this we can find out for which omega, if we know already the iteration matrix, we can Jacobi iteration actual matrix, we can find out the Jacobi iteration matrix eigenvalue and find out for which omega we should have the least value of lambda, or that will be the, or the SOR eigenvalue has least smallest spectral radius, then we will say that this is the optimum omega. The converse is also true. If mu is an eigenvalue of Jacobi iteration matrix B, or and a scalar lambda is there which satisfies lambda plus 1 omega minus 1 whole square is equal to lambda omega square mu square, then lambda is an eigenvalue of SOR iteration matrix. The proofs are complex, we are not discussing here. Using the above relation, we can find out the optimum successive over-relaxation factor omega oft, which is obtained as omega oft is 2 by root over 1 minus 1 plus root over 1 minus rho b whole square, which is the, this is the spectral radius of the Jacobi iteration matrix B from the same problem. Now, what we will do, we will continue the numerical experiment with what we did earlier with different value of omega for Gauss-Seidel, and what we can see is that the case for which Jacobi 20 into 20 matrix, Jacobi needed 709 steps, Gauss-Seidel needed 374 steps. For varying omega, omega 1.2 it is 258, omega 1.8 it is 133, omega 1.5, 1.8 it is 83 steps, from 374 it came down to 83 steps, again omega started increasing here. So, omega optimum should be in between 1.5 to 1.9 here, and what is happening in the spectral radius at 1.8, the cases we observed, it is giving least spectral radius. Like for Jacobi the spectral radius was 0.98, Gauss-Seidel the spectral radius is 0.97, omega 1.8 spectral radius is 0.8, and that is why convergence is faster. We look into the larger matrix 40 into 40 matrix, Gauss-Seidel is 0.99322 and Jacobi is 0.99661, the number of iterations are 2400 or 1291. Omega 1.8, the spectral radius is 0.92 and the number of iteration is 160 is minimum. So, again if we look varying omega for a 10 by 10 matrix, the least comes at omega 1.5. For 20 by 20, the least value comes at omega 83. here at omega 1.8 again. So, there is an optimum SOR factor for which number of iterations are less, and this we can calculate using the formula we have given earlier, that for 10 it is 1.51, where we will get the least spectral radius, for 20 it is 1.7, for 40 it is 1.84, and these are the values for which we get least spectral radius. After that the spectral radius will increase as well as number of iterations will increase. However, we can reduce the spectral radius significantly using successive over relaxation, and that is how we can reduce the number of iterations also substantially. So, we try to cover few important basic iterative methods. We will look into more complex iterative methods which gives faster solution, and also see in the iterative methods which work for non-diagonally dominant matrices in later classes. Also, another important thing which we will look is how to write computer programs using these iterative methods. The programs actually which have been used for the numerical experiments in this purpose, how can we reproduce these programs through these methods. Thank you.